Alright, in the past couple of slides, we discussed the different types of SQL injection vulnerabilities. Now in this section, we'll discuss how to find SQL injection vulnerabilities. So imagine you've been given an application and asked to test it. How would you go about testing the application to see if it's vulnerable to any SQL injection vulnerabilities? Before we cover that, it's worth mentioning that the methodology used for finding SQL injection vulnerabilities differs from one person to another person, and it's usually developed by experience. So just because I give you my methodology doesn't mean that you have to follow it to the letter. Instead, I would recommend that you take what is useful for you from it and then build and add on to your own methodology as you gain more and more experience in pen testing web applications. Okay, so finding SQL injection vulnerabilities, I've decided to split this into two categories depending on the perspective of testing. And the two categories are black box testing and white box testing. For those of you that have never heard of these terms before, black box web application pen testing is when the tester is given little to no information about the system. Usually the only information that the tester has access to is the URL of the application and the scope of the engagement. So this is similar to mimicking an external attacker that is trying to attack your system. The attacker usually doesn't know anything about the application other than the main URL of the application. Now for white box web application pen testing, it's the complete opposite. The tester would be given complete access to the system, including access to the source code of the application. Now there's a third category that I haven't included on the slide, and it's called gray box web application pen testing. This is a combination of white box and black box pen testing where the tester is given limited information and access to the system. For example, instead of just giving the tester a URL of the application, like you would with black box pen testing, the tester is also given accounts to the application. So when it comes to my methodology of finding SQL injection vulnerabilities, I loop both gray box and black box pen testing into one category, and that's because my methodology is the same regardless of the category. The way I see it is if I'm approaching it from a black box perspective, my scope will be much more limited than the gray box perspective unless I find authentication bypass vulnerability. Nevertheless, the methodology is still the same for finding SQL injection vulnerabilities, whether I'm doing it in public or an authentication page. And that's why they're looped in together. Now, when it comes to white box pen testing, that's a whole different methodology because you actually gain access to the source code of the application. And reviewing source code is a whole different realm than approaching an application from the outside. All right, let's start off by talking about how to test applications from a black box perspective. The first thing that I do when testing an application is map the application. And what that means is I literally visit the URL of the application. I walk through all the pages that are accessible to me within the user context that I'm running as. I make note of all the input vectors that potentially talk to the backend. I understand how the application functions. I try to figure out the logic of the application. I try to find subdomains in the application. I enumerate directories and pages that might not be directly visible to me through the application, and so on. And while I do all of that, I have my burp proxy listening silently and intercepting all the requests that I'm making to the application. So mapping the application is such an underrated step when it comes to pen testing applications, although I would argue it's probably the most important step. And the reason I say that is because I usually see beginners in this field get way too excited about the fact that they're testing an application, and then the first thing that they do is start throwing potentially malicious input vectors into the application to see if the application responds in an unusual way. And although this is a valid way of testing an application, it doesn't make you any different from an automated tool. So this is exactly what web application vulnerability scanners do. They crawl the application, they locate all the input vectors, and then they throw a ton of malicious payloads at these input vectors. And depending on how the application responds, the scanner logs the behavior as a potential vulnerability. And this way of testing usually only discovers the low-hanging vulnerabilities. So if you're doing exactly what a scanner can already do, then your testing is really not adding any value. Instead of doing that, what I would recommend is you leave that up to the scanners and instead spend quite a bit of time understanding how the application works, because most of the critical vulnerabilities found in applications are logic flaws that a scanner is not capable of finding on its own, or the vulnerabilities are embedded in pages that the scanner can't crawl, so technologies that the scanner can't crawl. Okay, so once you've mapped the application and you've listed all the input vectors that are potentially included in queries that are interacting with the SQL database, then it's a matter of fuzzing the application. And that's because we're looking for SQL injection vulnerabilities. You'd be fuzzing the application with SQL-specific characters. So what that means is you add special characters in the input vectors and see if the application responds in an unusual way. Now, depending on how the application responds, you start refining your query until you achieve your end goal. And that's what makes you different from a scanner, because a scanner just simply throws a bunch of input at the application. You as a human being you're capable of understanding the output of the SQL injection. And so you're able to refine your SQL injection using multiple requests until you actually achieve your goal. And we'll see how to do that in the exploitation section of this video. Okay, again, fuzzing the application means adding special characters and input vectors and seeing if the application responds in an unusual way. Now, that can be done in many ways. The first thing that I try to do is submit SQL-specific characters, such as the quote, or the double quote, or the hash, or the dashes that represent comments, and see if the application outputs an error. Now, errors are really important and really useful because they give you information about how the backend operates. So sometimes they give you the database that you're using, they give you the version of the database. We discussed that sometimes they actually give you the exact query. If they gave you the query, then you hit gold, because this way you don't have to develop your payload across multiple requests. Instead, you already know what the backend query is, and so you just develop your payload based on that query. And so the first thing that I do is try to output an error. Once I have an error, I try to build my query using multiple requests. So I refine my query based on the errors that I get, and I build my query. Now, in certain scenarios, you don't actually get an error, like for blind SQL injection. And so you also have to submit Boolean conditions, such as, and or 1 equals to 1 and 1 is equal to 2, and look for differences in the application's responses. So if you can get the application to respond differently when you force a true use case versus when you force a false use case, that means it's vulnerable to Boolean injection. Next, I do the same thing as Boolean injection. Instead, it would be to trigger time delays in the application and then see if there's a difference in the time it takes to respond. So if you input a function that causes a time delay and you actually observe that time delay, that means that the application is vulnerable to time-based SQL injection. Last but not least, I also submit out-of-band payloads that are designed to trigger a network interaction with a server that I control. And if I get that network interaction, whether it's a DNS lookup or it's done through HTTP, that means that the application is vulnerable to out-of-band SQL injection. And if I don't get them, that means it's not vulnerable to out-of-band SQL injection. That's a high-level overview of my methodology when it comes to testing from a black box perspective. There's really 2 steps. First, mapping the application. So listing all the input vectors in the application, and then fuzzing the input vectors to see if I can find a SQL injection. And again, when it comes to fuzzing the input vectors, you can refine your requests based on the responses that the application gives you. Okay, next is white box testing perspective. So where you're given the source code of the application. In this case, the first thing that I do is I enable web server logging and I enable database logging. So enabling logging at the web server level will help because when you're fuzzing the application, like we did with black box perspective, it will generate errors on all the different invalid characters that you input into the application. And then that helps you to detect that SQL injection exists, and then also to refine your payload later on. Similarly, for database logging, I enable that because when I think that there's a SQL injection vulnerability and I enter a SQL injection payload in the parameter, I'd like to see how it was logged at the backend. And then depending on how it was logged at the backend, I can see what characters made it through and in what format they made it through. And then I could say with maybe a 90% accuracy that yes, this is vulnerable to SQL injection before I even look at the source code of the application. So once I have my logging enabled, the next thing that I do is map the application, just like I would with a black box perspective. So I'll start with the application's graphical user interface. I'll map all the visible functionality in the application, all the input vectors that potentially talk to the backend. Next, because I do have access to the source code, I'll also do a regex search on all instances in the code that talk to the database. And that really depends on how the application is programmed and then which database it uses and so on. But I would have regex strings that I look for in the code to see if I've missed anything that I haven't mapped from a black box perspective. And you'll see that there are certain pages that might not have been directly accessible through the main page of the application, and you didn't discover them through directory brute forcing. And so it's useful to actually look at the code and see if there's anything that you missed. Once I have a list of everything, what I would do is I would literally fuzz the application. So I would submit SQL characters that could potentially break the query. I will look at how they were logged using database logging that I enabled in the first step. And then based on that, I can usually tell if it's vulnerable to SQL code injection. And if I feel like it's vulnerable to SQL code injection, then I actually do a code review of that functionality. So for example, if I think the login page is vulnerable to SQL injection, what I would do is I will look for the login functionality, so the function that implements that in the code, and then I would do a walkthrough of that entire functionality from beginning to end, until I have confirmed that it is vulnerable to SQL injection in theory. And then to confirm in practice that it is vulnerable to SQL injection, then I would test it out. And depending on the response I get from the application, that means it's vulnerable to SQL injection. So again, that's my methodology. It doesn't mean that it's a methodology that you should follow. I do know people that would automatically just go into the source code and then do a search for insecure functions when it comes to parameterized queries and so on. And so if they find an insecure function, they'll start with that instead of doing kind of a hybrid approach of both black box and white box, which is the methodology that I described. Okay, in the past two sections, we talked about the different types of SQL injection vulnerabilities and how to test an application to see if it's vulnerable to SQL injection. Now, in this section, we'll talk about how to exploit SQL injection vulnerabilities in order to achieve your end goal. And that really depends on the SQL injection vulnerability that you're trying to exploit. We so far talked about 5 different types: error-based SQL injection, union-based SQL injection, Boolean-based blind SQL injection, time-based blind SQL injection, and out-of-band SQL injection. So in this section, we'll talk about how to exploit each one of these vulnerabilities. And we'll start off with error-based SQL injection. Now, as a reminder, we said error-based SQL injection is an in-band SQL injection technique that forces the database to generate an error, giving the attacker information upon which to refine a query. So successful exploitation of an error-based SQL injection is the fact that you can get the application to output an error. So there's really not much to exploiting this vulnerability. All you would do is submit SQL-specific characters, again, such as the single quote or the double quote, and you look for errors in the application. Now, different characters can give you different errors, so it's good to fuzz the application with the commonly known characters to generate errors. Next is union-based SQL injection. Exploiting this vulnerability is a little bit more involved. As a reminder, we said union-based SQL injection is an in-band SQL injection technique that leverages the union SQL operator to combine the results of 2 queries into a single result set. Now, in order for you to use the union operator, you have to follow the rules of the union operator, and there's 2 basic rules. The first one is that the number and the order of the columns must be the same in all queries. And the second one is that the data types must be compatible. So the query that the application is making and the query that you want to make have to satisfy these 2 rules. And so when you're exploiting union-based SQL injection, the first thing that you need to do is figure out the number of columns that the query is making. We'll talk about that in a bit, and we've got 2 ways of doing that. Next, you figure out the data types of the columns. We're mainly interested with string data because we want to extract things like usernames and passwords and so on. And so that's usually saved in string format. And so we need to find a data type that outputs string data. And this way we could output the data that we want to extract. And then once you've figured out the number of columns that the query is making and the data types of the columns, then you could use the union operator to output information from the database. Sometimes you don't actually get the data type that you want, and so it's a dead end. You can only extract, for example, integers or so on. So it depends on the SQL injection and the context that you're running with on whether you could actually exploit it to extract information from the backend database. Okay, so I said there's two different ways of determining the number of columns that are required in a SQL injection union attack. And one of the ways is using the order by clause. Now, this clause orders the result set of a query by a specified column list. So let's take an example. If you've got select the title and the cost from the product table where ID is equal to 1, and then you say order by 1, what that means is that you're ordering by the first column, which is by the title column over here. Now, the way to figure out the number of columns is to incrementally inject a series of order by clauses until you get an error or observe a different behavior in the application. So if I say order by 1, it'll order by the first column. If I say order by 2, it'll order by the second column. Now, if I say order by 3, that column doesn't exist. And so I get an error saying the order by position number 3 is out of range of the number of items in the select list. And so this way, I know that 3 is not a column. And since I incrementally increase the value of the order by integer over here, I know then the number of columns is this value minus 1. So 3 minus 1, which is 2. Number of columns that are being used in the SQL query is 2. So that's the way to do it using the order by clause. You could also figure out the number of columns required in a SQL injection using null values. So again, let's take example of a query that does select the title and the cost from product table where ID is equal to 1. And then you say union, select null, and then dash dash for a comment character. Now, because a union using the union operator requires that this query has the same number of columns as this query, if you don't use the same number of columns, you will get an error. So if you incrementally inject a series of union select payloads specifying a different number of null values until you no longer get an error, then you could figure out the number of columns that are required by a SQL injection. So for example, when I put this payload over here, which is the one over here, it'll give me an error saying something like all queries combined using a union, intersect, or except operator must have an equal number of expressions in their target list. So it's telling me you're using the union operator, but your two queries don't have the same number of columns. And so I know that the query does not have only one column. So I increase the number of null values again by 1. So now I have 2 null values, and I try it out, and I see if it gives me an error, that means it has more than 2 columns, and I try 3 and so on until I no longer get an error. Now, in this case, we only have 2 columns, and so this will output the results of this query over here and then the null values over here. So this won't give me an error, and that means that the number of columns that I have is equal to the number of null values that I entered, which is 2. So you could either do it by the order by clause or by adding union select payloads specifying different numbers of null values. Okay, so that's how to find out the number of columns that the query is using. Next, we need to find a useful data type in these columns. And so the way to do that is to probe each column to test whether it can hold string data by submitting a series of union select payloads that place a string value into each column in turn. So over here, what I would do, now I know that it has 2 columns from the previous exercise that we just did. So what I would do is I would add a string value, so A in the first column value, and see if it outputs an error. If it outputs an error saying that, I don't know, it's incompatible with a certain type. So in this case, we're saying that the first value is actually integer. And so I get an error saying that it's incompatible, which means that the first column is not a string data type. So next, I try the second column over here. So I keep this as null, and I try the second column. And if I get an error, that means this also does not accept string values. And I keep doing that until I find a value that allows me to enter string data. And again, in some cases, you might not actually find a value, and that's why some SQL injections allow you to do things like extract data from a database, whereas others, you're very limited in what you're, like the data type that you're allowed to extract. Okay, and so going back to the slide, explaining union-based SQL injection, we talked about how to figure out the number of columns that the query is making. We also talked about how to figure out the data types of the columns. If you have columns that are being outputted on the page and they use string data, then you could use the union operator to output information from the database. And that's how you exploit union-based SQL injection. Next, let's talk about exploiting Boolean-based blind SQL injection. The first thing to do is submit a Boolean condition that evaluates to false and note the response. I've got an error here. It should say note. The next thing to do is submit a Boolean condition that evaluates to true. And again, note the response. If the response is different, or when you force a false statement versus a true statement, then you have a Boolean-based blind SQL injection. And the way to exploit that, we already talked about that, is to write a program that uses conditional statements to ask the database a series of true and false questions, and then monitor the responses. If the response is the same as the response you got when it evaluated to true, that means the question that you're asking the application is true. If the response is the same as the response that you got when you forced the false statements, that means the question that you're asking the application is false. And that's how you extract data from the database when it comes to Boolean-based blind SQL injection. Next is time-based blind SQL injection. What you do is you submit a payload that pauses the application for a specified period of time. If the application does actually pause for that specified period of time, that means it's vulnerable to time-based SQL injection. And then it's a matter of doing the same thing that you did for Boolean-based SQL injection. You just write a program that uses conditional statements to ask the database a series of true and false questions, and you monitor the response time. If there's a delay in the response time, that means the question you're asking the application is true. If there's no delay in the response time, that means the question you're asking the application is false. And then you send a bunch of those requests until you enumerate or you extract the thing that you want to extract from the database. And we'll gain experience in all of these different types of SQL injection vulnerabilities, like hands-on experience, in the next upcoming videos. Okay, so exploiting out-of-band SQL injection. Again, a reminder, this is a vulnerability that consists of triggering an out-of-band network connection to a system that you control. And the way to exploit it is to submit out-of-band payloads designed to trigger an out-of-band network interaction when executed within a SQL query, and monitor for any resulting interactions. So this is database specific, obviously, so knowing the type of database that you're using will be very useful in this scenario. And it depends on whether the database has these functions enabled. And so if you do get that network connection, if you receive that network connection, again, whether it's a DNS lookup or something else, that means that the application is vulnerable to out-of-band SQL injection. And in certain scenarios, you might be able to immediately exfil data from the application, so directly exfil data from the application, whereas in other cases, you're again stuck asking true and false questions, just like you would for line-based SQL injection. Okay, I didn't want to end this section without talking about automated exploitation tools. So one of the famous ones, and it's open source, is a SQL map. It's a tool that is used to find SQL injection vulnerabilities. It's very, very powerful, and it's very customizable in the sense that you select what parameters you could inject. You also select the vigorosity of your testing. You also select the angle of your testing. So if it does find a SQL injection vulnerability, sometimes you have the ability to say, try to get a shell on the system, or try to dump the usernames and passwords of the applications on the system, and so on. And so this is a very important tool to look into when it comes to finding SQL injection vulnerabilities. Other tools that you could use, which are more for detection versus actually exploiting it to achieve your end goal, are web application vulnerability scanners. We talked quite a bit about these in this video. They're scanners that crawl the application and look for vulnerabilities. So not just SQL injection vulnerabilities, they look for all types of vulnerabilities in an application, and they usually report it as a vulnerability. They don't actually go all the way to exploiting it to get a shell on the system or to dump usernames and passwords. And some of these tools are open source, whereas others are paid. So something to look into. Of course, these tools have limitations and they operate from a black box perspective. So there are other tools that operate from a white box perspective. They're called static analysis tools, whereas these are called dynamic analysis tools. So something to look into when you want to automate a portion of your web application testing. Right. Now that you know what a SQL injection vulnerability is, how to find it, and how to exploit it, the next thing to learn is how to prevent SQL injection vulnerabilities. And that will come in really handy when you're writing pen testing reports and you need to provide recommendations to your client on how to remediate the vulnerabilities that you discovered. So there are the primary defenses and the additional defenses, which use the concept of defense in depth. We'll talk about each defense in the next couple of slides, and those are the ones that are mentioned in the Web Application Hackers Handbook. But the idea is I have this highlighted over here because this is the correct way of preventing SQL injection vulnerabilities, and that is by using prepared statements or parameterized queries instead of string concatenation within a query. All the other options are partial options and should be used only as a last resort with the knowledge that they might be bypassed or they might be implemented incorrectly and they might cause a SQL injection in the future. And so let's talk about each one in order, starting with the correct way of defending against SQL injection vulnerabilities, and that's using prepared statements. Okay, so let's take an example first. So you've got a code block over here. The first one, which is query over here, has select the account balance from the user data table, where username is equal to request.getParameter customer name. So what this does is it takes user input, so user controlled input customer name, and it adds it directly to the query, and then it defines the structure. So it's defining the structure of the query, and then it executes the query. So do you spot the issue over here? It's a bit obvious. The user supplied input customer name over here is embedded directly into the SQL statement. And so anything that the user adds over here might actually be interpreted as a part of the query. Okay, so using prepared statements can prevent SQL injection attacks, and that's because the construction of the SQL statement is performed in two steps. The first being the application specifies the query structure with placeholders for each user supplied input, and then the application specifies the content of each placeholder. This way, there's no way that a user supplied input that is specified in this step over here can ever interfere with the structure of the query in this first step, and that's because the query structure had already been defined, and now any placeholder data is interpreted in a safe way as literally data versus SQL code. And so let's take an example of code that is not vulnerable. So in this code over here, you could see there is the variable cust name. It takes an user supplied input, customer name. We've got the query over here being defined, and then over here it prepares the statement through a database connection. So the prepare statement method is invoked to interpret this query and fix the structure of the query, and then the setString method is used to specify the parameter's actual value. Now, because the query structure has already been fixed in the prepared statement, this value can contain any data without affecting the structure of the query because it will literally be interpreted as data versus as part of the query. So if the user over here had put in SQL characters like a quote or a double quote or so on, that will be interpreted as data, and it can't ever change the structure of the query because the structure has already been determined and fixed. And that's how you prevent SQL injection vulnerabilities. That's the correct way of preventing SQL injection vulnerabilities. Now, there are partial options that the book talks about. One is the use of stored procedures. So stored procedures are batches of statements grouped as a logical unit and stored in a database. This is not always a safe way of preventing SQL injection vulnerabilities because if it's implemented incorrectly, it could still be vulnerable to SQL injection. So it still needs to be called in a parameterized way in order for it to be safe against SQL injection vulnerabilities. And the reason that some people would use stored procedures or any of the partial options is because there are certain parameters that you can't specify as placeholders in parameterized queries. And for example, the table name or the column name. And so if that's user controllable, you have to use one of the partial options in order to prevent SQL injection attacks. Now, the correct way of doing it is that this should never be user controllable, but if it has to be user controllable, then you use one of the partial options. That's option 2. Option number 3 is whitelist input validation. So define which values are authorized. Everything else is considered to be unauthorized. And we talked about parameters that can be placeholders like the table name and the column name. In this case, a whitelist input validation would be you know exactly the column name should be or the table name should be users, and so you only accept the value users and nothing else. And this way you prevent the attacker from injecting other characters or other strings could potentially interfere with your query. Option number 4 is escape all user input. So validate user input, and that should only be used as a last resort. Again, it's a partial option versus something that for sure prevents SQL injection vulnerabilities. Okay, additional defenses. Before we talk about that, let's talk about the concept of defense in depth. So the idea is to make it as difficult as possible for the attacker to compromise your organization. And that's done by providing additional protection in the event that the frontline defenses fail. So if me as an attacker, I want to gain access to your organization and I manage to get past the first block that you had put in my way, then I would have 2 other obstacles that I need to get through before I get to your organization. And so in the same sense, although you use parameterized queries, just in case you by chance forgot to include it on one parameter in one page, you want to have defenses in place that if a SQL injection vulnerability was exploited, the attacker gets another obstacle in their way before they could achieve their goal. And so one is least privilege. So the application should use the lowest possible of privileges when accessing the database. And the reason behind that is if SQL injection exists in your application and an attacker exploits it to gain remote code execution on the server that the database is installed on, then the attacker will gain the same level of privilege that the database is running with. And so the database is running as system or root, then the attacker already has all the privileges that the attacker needs on that server. However, if it was running with a service account that has all the privileges stripped, then the attacker has to find ways to escalate privileges on the server before they can, for example, move laterally within the organization. And so the application should always use the lowest possible level of privilege when accessing the database. Any unnecessary default functionality in the database should be removed or disabled. That includes things like functions that allow you to execute system commands from the database, also functions that allow you to make a network connection that we talked about out-of-band SQL injection, right? So functions that allow you to do that. So any unnecessary default functionality that you don't need for the application to function, that should be removed because it decreases the amount of things that an attacker can use in order to penetrate your organization. Ensure CIS benchmarks for the database in use is applied. So there are benchmarks for most of the databases out there, and these are rules on the way to configure your database in order to ensure that it's secure. And it includes things like the application should use the lowest possible level of privilege and removing any default functionality and so on. And last but not least, this one's obvious, all vendor-issued security patches should be applied in a timely fashion. So if you get notified that the database version that you're using is vulnerable to some kind of vulnerability, then you should patch your database as soon as possible to decrease the window of time that the attacker has to attack your database and to exploit the vulnerability. And then this one, we already discussed it. So whitelist input validation. So although you have parameterized queries, an additional defense, so a defense in depth, is to still whitelist all the input values that come from the user, so come from the client side. Okay, and that wraps up the last section.